Okay, thanks for coming out. It's an 8 a.m. class. It's a pretty crappy time, especially for a fourth year course. So if you're here, I appreciate you coming. I don't have a choice, but you guys certainly have a choice to come, but I appreciate you coming. If you happen to miss any lectures, I'll be posting my video. I'm actually video recording in real time, so I'll be posting them on YouTube. So if you'd like to catch up or if you want to review before the midterm or whatever evaluation you have, then by all means, I'll be posting YouTube links on our course website. Okay? So welcome to Intelligent Systems, or I like to call it machine learning, because if you go to an employer and they ask you what kind of relevant courses you've taken, Intelligent Systems is a little ambiguous. If you say machine learning, they're going to know exactly what you're talking about, because it's one of the biggest topics you can get into in industry. Big data, data analysis, machine learning is a really nice, it's a big topic to get into. So my name is Ray Fan. I did all of my degrees here at Ryerson. I did my bachelor's, master's, and PhD all here. I graduated in 2013, so it's nice to come back and teach a second time. So I see some familiar faces, but if not, then this is who I am. And we'll be convening every Wednesday from 8 to 11, so there's only one lecture a week, but it's for 3 hours. We're gonna meet up here once a week, except for reading week and all that. If you guys like to pick up some course outlines, by all means, please do so. And lab times, they don't start till the next week, so don't go to any labs this week. Obviously, they're gonna start next week, so just check your course schedule and see which lab sessions you're in, and then you can double check with the course outline as well. So machine learning is basically the science of getting computers to act without explicitly being programmed. So you've probably used a lot of machine learning applications without even knowing it, such as when you're in your email, there's such thing as a spam classification tool where you probably don't want to see any emails about enlarging your penis size or trying to gauge you into winning the lottery. Those emails are probably not in your email box because of spam classification. They're designed to throw those emails out so they don't bother you. Okay, so that's one application. So we're going to be learning a lot of different things in this course, and hopefully I'll be able to teach you the basics, so when you go into industry you'll be able to start running off the ground, or start off the ground running. Okay, so in terms of course prerequisites, this course will be a little mathematical, so there's going to be a little bit of calculus, a little bit of linear algebra involved, but I'll make sure I go through those slowly so you're up to date. And there will also be programming involved. So lab assignments that you will be carrying out in this course, they do require the MATLAB programming language, so if you aren't familiar with that language, then there will be tutorials posted on my website that'll get you up to speed. But they will be using the MATLAB programming environment, and most of you have probably used it, because especially with your third year courses on that, so we'll be building on those skills. Okay, so to get MATLAB, it's easy. Just go to e.ryerson.ch/MATLAB, and there's steps for you to download the software on your computer. And the big question is textbook. There are no textbooks for this course. They're not required. Especially last year, the required textbook was this one, Pattern Classification by Duda and Hart. It was like $250, and I don't think you guys want to shell out that much money for a book. So textbooks are completely optional. If you want to get a textbook for yourself, then you can consult any of these references on the course outline. They're more than good. They're more than sufficient to get you, to have supplemental material. But any course material that's covered will be done completely through the lecture notes and examples and supplementary material that I'll be posting. So there's no required textbooks in this course. So you can save your money. Okay. So course structure. There's also lab assignments. If you're in the undergrad stream, ELE 888, you can do in pairs of 2. If you're in the graduate stream, you should have enough skills to do it alone. So if you're in the graduate program, you have to do it alone. If you're in the undergrad, you can do it with pairs of 2, or you can do it alone. It doesn't matter. But in the graduate stream, you have to do them alone, because that work is expected of you. Okay, so the lab assignments, obviously you have to do them. You can do them in the lab, or you can do them offline. But the labs are due in class on certain days. You can take a look at the course schedule to figure out when the actual labs are due. You just hand them in class, and yeah, so you don't have to go to the lab. By all means, you can. The TA will be there to guide you and have answer any questions that you have. But the labs, you hand them in here, and then next week you'll get them marked. Okay, so course evaluation, it's split 50-50. So there's a midterm and final exam. The midterm is 20%, and that'll be the Wednesday after the reading week. So the week before, we'll do a review, and then you have the reading week to study, and then you'll have the midterm following that. Final exam is 30%. I don't know what the day is. They'll tell me probably sometime in late March, and I'll post it online for you as soon as I find out. And then the lab components are 50%. So labs 2 and 3 are more heavily involved, so they're weighted a little more, and the first and the last lab are a little less because they don't require much work. and especially the last lab, you don't want to do that much work towards the end of the semester. So the due dates are here. You can check them out, but they're due in class. You hand them in before I leave, and that's that. Okay. Here's the detailed course schedule. By all means, you're more than welcome to check that out. But I should be able to cover all the topics that I've outlined in the course schedule. It might be subject to change depending on how slow or how fast I go. I might introduce more, I might introduce less. It just depends on how fast I go. So you're more than welcome to check that out. So you can check, when the lab is due on the right column, and then you can see which lab is covered for the first, for the week that you're in, and then the material is covered each week and so on. Okay, so all the material will be posted on Blackboard. So if you go to the course website, here we are. So if you just go to content, and then pretty much everything here that you need. So you can go over you also the calendar if you need to figure out when things are due. And then everything that you need to know is posted in the table of contents. So any lecture notes that I do will be put in PDF, will be posted on the course website. The links to the lectures, the YouTube links will be posted under video links, and then the lab assignments, I'm still working on the first one. It should be done by the end of today. You'll be able to see that first assignment there. And then some other useful links, like some links to other courses that deal with machine learning that you might want to take a look at, and other cool YouTube video links that deal with that topic. And then important documents are like the course outline, the course schedule. If you're handing in an assignment, you need to hand in the cover page that goes on top, and all the other important documents are there. So you can peruse at your leisure. Okay, so now that's done. Let's get started with the actual stuff. All right. Okay, so course overview is done. So let's actually get to the actual material. Okay, so general concepts. So you've heard machine learning. It's a buzzword that's floating around. So what exactly is machine learning? What is the actual topic? So there are many different versions of the definition that you might hear, but the two that stand out for me about machine learning are from as follows. So what is machine learning? So there are many definitions. Oh yeah, by the way, my writing looks like a piece of crap, so if there's something that doesn't look clear, please let me know, and I'll try to write as best as I can, but my writing is pretty much chicken scratch. So there are many definitions that stand out, but the two that I believe in are. Okay, so the first definition was a guy, a research scientist by the name of Arthur Samuel, and he made this definition of machine learning in 1959. And it's the definition that I mentioned earlier on as we were introducing each other. So it's the field of study that gives computers the ability to learn and do tasks without explicitly being programmed. So you program it and give it a set of rules that it follows, and then it figures out what to do and how to actually solve a problem by itself. All right, so that's the bare bones definition. So it's a field of study, that gives computers the ability. By the way, if you want, you can certainly write things down, but I'll be posting these online, so it's up to you whether or not you want to write things down, or if you don't want to write them, that's totally fine. Being explicitly programmed. So one of the early success stories of machine learning is this guy. He decided to write a program to try and automate playing checkers. So what this guy did was he made a program where it played tens of thousands of games with itself. So it would make moves, and then it would alternate back and forth, and it would remember which moves led to wins and which moves led to losses. So then it would remember all those choices and build a prediction model where the next time you played against the computer, when the opposite team made a move, it would figure out the next move it would make with a high probability of winning. So it was probably one of the biggest success stories of machine learning at the time. So it had the patience to play games with itself, tens of thousands of games, and then finally it had a nice prediction model where, given the state of the board and the move that the previous player made, what is the move I need to make to have a high success of winning, a high probability or high success rate of winning? Okay, so that was a pretty cool machine learning application, one of the earliest ones that I can think of. So let's see here. So vigorous, here we go. So Samuel, can't write. Samuel wrote a program to play checkers. All right? Okay, so the program play thousands of games with itself. Playing with yourself is a little dirty, but in this case, it's very, very academic and it's very professional. All right? It's all for the sake of research. All right, thousands of games with itself. So the program remembered which moves led to wins and which moves led to losses, and it built a model based on that. And given the board and the previous player's move, it would figure out the next move with a high probability of winning. All right, so the program remembered the board moves that led to wins and losses. Okay? So after, sorry, that's it, looks like a Q. When playing against the program, it would choose, let me just move to the next page, running out of room here. Choose, sorry, let me scroll up, I guess you were writing this down. The next move with the best chance of winning. If you want to look it up in Wikipedia, it's called the mini-max strategy. So whatever, so it's basically simulating thousands of simulations, and it chooses the move with the highest probability of success. So it branches off what is known as the mini-max strategy. All right, so best chance of winning. Okay, given the current state of the board. Okay. Okay, so that's the bare bones definition. So that was 1959. And the next definition was created by a guy named Tom Mitchell from Carnegie Mellon in 1998. And it's a little more broad, but I'll certainly cover it here. It actually does apply to many machine learning problems that you see in practice. So the next definition is by Tom Mitchell in 1998. So the definition is you're given three things. So you're given 1, an experience, 2, a task, and 3, a performance measure that measures the performance on the task that you're trying to do. Okay, so given an experience, I'm going to call it E. So E, right? And then a task. That task is T. And finally, a performance measure. P. All right? So this definition might be a little confusing, but if you parse through the words, it actually does make a little sense. So machine learning is given a computer program okay, it learns from the experience E with respect to P and T, so the performance measure and the task. So the task and the performance measure. Oops, P. Okay. If T measured by P improves with E. A lot of different characters here. So it's a computer program where it learns from a particular experience, and then with respect to a task and a performance measure where if you measure the performance of this particular task and if it improves with respect to the experience E, then that's a machine learning problem. All right, so just to draw on an example, especially the checkers example. Okay, so the experience will be the amount of games that it played with itself, so the tens and thousands of games that it decided to play with itself. So that is the experience. Okay, so the experience, okay, would be the program, program playing thousands of games with itself. Again, it's for the sake of academia. It's nothing underhanded, nothing in the subcontext here. Okay, the task is to play checkers. And the performance measure is the probability of winning a game given the current state of the board and the previous player's move. Okay? So the performance. So which makes sense because if you have a machine learning program and the program keeps winning and the probability gets higher, then that's probably, it's a good definition of a machine learning problem. So the probability of winning, let me go full screen. Where are we? It's a little better, thanks. Probability of winning the next game of checkers against a human player. Okay, that's nice. Okay, so that's a nice definition of machine learning, so let's go a little deeper. So in machine learning, you can split up problems into predominantly two different categories. There's one problem which is called the supervised learning problem, and another which is called the unsupervised learning problem. So even though there are two letters that make the word different, they're actually completely different problems, and we're gonna go through what they are right now. Okay, so there's two different classifications of machine learning problems that you'll see in practice. Okay, so in machine learning, there are two common categories that problems fall into. It used to be supervised learning back in the day, but now because of the big data, the analytics push, the unsupervised is actually very popular these days. So there's supervised learning problems and unsupervised. So sorry, this is an R, unsupervised. Okay, let's go into this in a little more detail. At least the first one. Okay, so there's supervised and unsupervised. So there's two different machine learning problems. So supervised learning. Basically what supervised learning is you are the teacher, and what's happening is given a machine learning problem that you want to solve, your job is to collect a bunch of data that are related to the problem of interest that you're trying to solve. So you have a bunch of data, and then each data point has an expected output. So for example, if you're dealing with spam classification, the email would be the data, and the expected output would be whether or not the email is spam or non-spam. And the goal is to create a predictive model based on that data where it should be able to correctly identify whether an email is spam or non-spam, given that you've submitted a data point to it. So you are training a model to be able to predict new data that comes in, whether or not it belongs to spam or non-spam, or predict whatever you want. So supervised learning is you are teaching something or teaching a program to be able to classify or predict things on its own, given that you have example data with expected labels. All right? So supervised learning in one sentence is you are trying to create a prediction model. Okay, you're trying to create a prediction model from labeled training data. It's called training data because you are using this data to train a model so that you're able to correctly identify other new data points that come into the actual algorithm. Okay, so create a prediction model from labeled data. Okay, so let's go into a little bit more category. I'm inside category. Let's go in a little bit more vocabulary. So so this is labeled, and I like to call this training data as well. So this is training data as well. Okay, so what exactly is training data? Well, training data is data that you collect that is based on the problem that you're trying to solve. So it's example data that you've collected that has a bunch of data points with expected outputs. So this is what you know beforehand. This is information that you know beforehand, and you're trying to create a model based on that data. So training data is data collected from the problem you're trying to solve. Okay, the problem you're trying to solve. And, okay, that's fine. And then each sample, training data consists of samples, of course. Okay? So each sample has characteristics about the problem that you're trying to solve. So You want to choose characteristics that are unique to the problem that you're looking at. So for example, for spam classification, you have emails that are the data, and you want to look at specific features that stand out to figure out whether or not you want to classify the email as spam or non-spam. So the content of the emails, words, the frequency of the words, the IP address of the user who sent it, the location of where the user sent it, or the content of the email, sender, receiver. So there's a bunch of different features that you can choose to make it stand out as to whether or not the email should be classified as spam or non-spam. All right, so it consists of samples, okay? Each sample has a set of features. Okay, and a feature is something that is unique and that is characteristic to each training sample or each sample that you're looking at. So spam or non-spam, for example, or if you're in real estate, if you want to predict the housing price for a particular house that you're trying to sell, features could be the square footage, the location of where the house is, the demographics of the different people who live there, the number of bedrooms, if you have a pool, that kind of stuff. So each feature is unique to that particular problem that you're trying to solve, and obviously the more features you have, the better your classifier or the better your prediction algorithm will be. Okay, so each feature is a unique characteristic that describes an example. Okay, so you have a set of inputs and then you also have an expected output or expected label for each data sample that you have. Okay, so the output value or the output label is the right answer given the features. Okay, so your objective is to create a prediction model where, based on the training data, which has distinct features and a correct label, your job is to figure out a prediction model that will accurately classify new, or not actually predict new instances that come in. Okay, so an example would be the spam classification in your email. Okay, so the training data would be emails. Actually, what Google does is sometimes when you get email that is unwarranted, sometimes the spam classifier doesn't work and you'll get like a really bad email in your inbox. You have the option of marking the email saying this is spam. So when you do that, you're telling Google that yes, this label means that this email is spam, and they collect all the different data from all the different users and they actually retrain their spam classification algorithm so that it adapts to new emails that come in. So it's actually quite a smart algorithm, and we'll talk about that later. So training data, emails. All right? And then you also have features, which are, it could be words, features. So words, the subject, win $1 million now, or enlarge your thing size, right? So you probably don't want that stuff in your email. The sender, the IP address, and so on. Okay? And the output label will be whether or not this email is spam or non-spam. Okay? So output label. Spam or non-spam. Okay? Another example would be real estate. Let's say you want to predict the price of a house. How would you do that? Well, you'd use different features: square footage, whether it has a pool, how many rooms there are, whether there's a den, and so on and so forth. Right? So training examples. Just house information. Okay? And then the features would be, square footage, does it have a pool? Close to a school, and so on and so forth. So all those factor into the price of a house, right? Okay, and then finally the output data, or the output labels, would be the actual price. as you can see here, these are two different prediction problems, but the output labels are different. So spam and non-spam, they're discrete labels. So it's either 0 or 1, and the price is a continuous label. It can be from 0 up to, you know, a million or so, right? So they're two prediction problems, but they have two completely different outputs. All right? So once you have your training data, the objective next is to create a training model, or to create a prediction model. All right, so prediction model. Okay, so the goal is to take a look at the training data and to figure out the best prediction model that would be used to be able to accurately predict or classify things. All right, prediction model, so goal is to analyze the training data and to create what's known as an inferred function or prediction function, to create an inferred function. All right? So this function or this prediction model will be used to classify or to predict new data points that come in, points that you haven't seen before that were not part of your training data. Okay? So this function is used to predict the outcome of new instances. So an instance is a new data point that you haven't seen before. That's part of your, you know, that you want to classify or that you want to predict that were not seen before. Okay? So this is usually called the test data. So in machine learning parlance, they usually split things up into training data, so the data that's used to train your model, and test data, the data that wasn't part of your model, but you want to be sure that it accurately predicts or classifies that data. So because you don't want it to be part of the actual model. You want to be sure that it generalizes. Okay, so just one last thing before we get on to some other stuff. So basically, so therefore, supervised learning. So this is the definition that you should remember when you get out. Supervised learning is concerned with creating a good prediction model given training data to predict outcomes of new instances. So that's pretty much what supervised learning is. So you're the teacher, you're trying to create a nice model to be able to predict or to classify new data that comes in. All right, so that's the bare bones definition. Okay, so that's supervised learning, and then there are two subcategories of supervised learning. So one category is called regression, and another category is called classification. So the difference between the two is classification, you're trying to predict the output to belong to certain discrete groups. So for example, if you are taking a look at cancer patients and you want to take a look at a tumor, you want to classify it as either benign, which is good, or malignant, which is bad. So that's one problem with supervised learning, where you're predicting based on putting them into separate groups. And then another category I talked about is regression, where you're trying to predict a continuous output. So for example, if you want to predict housing prices, it varies between 0 and any real number that's above 0. Okay, so there's an infinite number of groups. Okay, so supervised learning is split into two groups. Yeah, I'm gonna try to take a break every hour. So you know, just to be sure that, you know, we're fresh. So I'll try to take a break every hour. So supervised learning is split into two groups. One, it's regression. Two, classification. So regression is not used that often. We actually tend to go to classification a little more, especially because it's a little more applicable to what we're doing. But nevertheless, we will cover it here. So regression. What regression does is that it predicts continuous valued output. Okay, so the output can belong to an infinite number of many groups. Okay, so for example, you have housing prices, right? So this data was collected by one of, I don't know if you heard of him, his name's Andrew Eng from Stanford. He also heads up Coursera, which is an online platform for free courses. One of his students actually collected a bunch of housing price data from Portland, Oregon in square footage. So this is just one example. We're using one feature, but this is housing prices. So you've got size of square feet on the x-axis, and you have the actual price of the house in y. So the objective here is to find a nice line of best fit that'll fit through all the points. You're trying to find some sort of pattern where you're able to fit a line of best fit through all these points. And given this line of best fit, you have the right parameters to predict what housing prices would be within, with data that wasn't part of the actual training set. Okay, so the housing prices here. So we've got the x-axis. So we've got training data. Of square footage. Sorry, I'm trying to write a squared here. And the goal is to find a line of best fit and predict the price. Like for example, you can see there it kind of follows like a square root function or maybe a quadratic function, so something like this. Maybe it might fall something like this. And if you wanted to predict, let's say, what the price would be at 750 square feet, somewhere along here, then it's probably looking at about maybe 225,000. So something like that. Right, so the goal is to find a line of best fit that fits through your training data and to accurately, or not accurately, but to best predict what the outcome would be given that given that training data. All right? Okay. So that's regression, and then classification is used a lot more. So we're going to cover that now. Okay. So the goal of classification is to predict discrete valued outputs. So that's the difference between regression and classification. So one is continuous and the other is discrete. All right? Okay, good. Just checking my time here. Okay, so examples would be, spam or non-spam, yes or no, 0 or 1, or if you want to figure out whether an object in an image belongs to a certain set of groups. So it doesn't have to be 0, 1, it could be 0 or 1 up to n. So it doesn't have to be 2 classes, it could be multiple classes if you wish. So examples, okay, we got 0 or 1, spam and non-spam, yes, no, and so on and so forth. Or you can go from 1 up to n, right? So that's also, positive, negative. That's applicable as well. So this is when you want to predict whether a data point that's coming in belongs to a discrete number of classes, all right? So this is when you want to predict whether a new instance belongs to a particular group. Okay, so the prediction model here is also known as a classifier because you're trying to classify a point to belong to one of a certain amount of groups. So the prediction model is also known as a classifier because you're trying to classify whether or not the point belongs to a certain number of groups. Okay, so a good example would be, let's say you're taking a look at breast cancer or some sort of cancerous tissue in your body. And so let's do just breast cancer, I suppose. Okay, so the goal of this is to determine whether or not a patient has a benign or malignant tumor. Okay, so determine whether a tumor is benign or malignant. So benign is it's the tumor where it doesn't really do any harm, but it's just there. It's just a mass, right? So benign, I would say that it's good in the sense that it doesn't really do anything harmful, or malignant, which is bad. Okay, so for example, let's just use one feature for now. So let's say we're going to take a look at the size of the tumor. Right. Usually, the bigger the tumor is, the more likely that the tumor would be classified as malignant. Okay, so for example, we have something like this. Okay, and let's say this is yes and this is no, 0, 1, right? And let's say we want to use the tumor size as the feature, okay? And then you might have some tumors that are like, some tumors that vary in size and they're marked as no, so the X's mean that it's no, and there might be some tumors that might be yes. So unfortunately, you got some here, for example. Sometimes you might have some tumor sizes that are a little bigger than one that you find that's malignant, but it's benign. But that's, it's just the variability of the data, okay? And the goal is to figure out what's known as a decision boundary. You want to draw a line that separates between the two classes. So anything that's on one side of the line will be classified as benign, and anything on the other side will be classified as malignant. So it's a different problem altogether. So instead of finding a line that best fits through your points, this case you're trying to find a line that best separates the 2 points into 2 different classes. And then anything on one side is one class, anything on the other side is another class. So it's a different problem altogether. Okay? So let's see here. So you want to find the line that best separates the 2 classes. Okay? This is what is known as the decision boundary. So we're going to talk about decision boundaries later on in the course. But for now, you can take that. You can take that in your head. So this is what's known as the decision boundary. So the best decision boundary might be something along here that has the least amount of misclassification error. So, but it's the best fitting line. So this is what's known as a decision boundary. Okay, this is just one feature, so sometimes you might have 2 features where instead of using just the size of the tumor, you might want to consider the age of the patient as well. So usually when a patient is older, they're more likely to have, have cancer, unfortunately. So in this case, let's say you have 2 features. So let's say you've got 2 features now. And then you have tumor size on the X and age on the Y. And then you might have groups that look like this. So this might be classified as benign here. So this is benign. Oopsie, I can't spell. And this side might be classified as malignant, I guess. Something like that. Okay, and the best decision boundary will obviously be something like this. That's the decision boundary, and that's the best line that will separate between the 2 classes. So anything on one side will be benign, and anything on the other side is malignant. So that's the goal. Okay, so usually you want to use more features. 2 is not enough. You might want to consider maybe the clump thickness or the uniformity of the cell size or the uniformity of the cell shape. You want to use more features that are discriminative in order to be able to classify between the tumors. Okay, so we usually want more features to help further discriminate between benign and malignant. It's generally you just don't use 2. You try to use as many features as possible. So choosing the right features is, unfortunately, it takes a lot of trial and error and experimentation. You just have to keep trying a different set of features until something works. So a lot of machine learning is actually experimentation, and the rest of that is to justify why your experimentation works. Okay, so choosing the right features is challenging. It takes experience, experimentation, and just good old luck. All right? Okay, so that's all I got to say about unsupervised learning. So it's a task that we can pretty much relate to. Okay? Now we're going to get on to the next category, which is unsupervised learning. Okay, unsupervised learning is a little different. So what you're given is you're given training data, but you're given absolutely no information about their labels. So you're not given whether or not it's a yes or no, spam or non-spam or whatever. You're just given a bunch of data points, and your task is, okay, figure out some structure for me. Can you separate these into different groups? Given this data, which I absolutely know nothing about, can you find some patterns in this data, or can you group these into certain categories by yourself? That's what unsupervised learning is. All right? So unsupervised learning is given training data with no labels, with no upload labels. So you don't know if it's yes or no, spam or non-spam, and so on. Okay? Figure out if the data can be grouped in certain categories. Okay? So each group is going to have something in common with each other. So each group has things in common. Okay? So if you remember supervised learning, you had data which had clear distinct points, right? So something like this. So in unsupervised learning, you're not given any labels. So something like this. So we're not given any labels. So if you remember the tumor stuff we were talking about, what it would look like, it would just look like this. You have a bunch of data points like this. Right? So this is tumor size, and this is age. But you're given no labels. So what you have to do is, given this data, can I separate these into groups that have distinct similarities between them? So yeah, so if you look at this, you can say, yeah, so maybe this might belong to one group, right? This might belong to one group, and this might belong to another group. And then once you, this is what's known as clustering, where you're clustering different data points together into different groups. And once you achieve these groups, you can take a look at what's actually common. So, for example, in this group, you know, they more or less have the same tumor size or the same age group for the particular patients, and the other side might have, you know, a different dynamic range. So the goal is to try to separate data into groups by itself, and then you can look at the groups and figure out what's common between them all. Okay, so this is what's known as a clustering problem. So, we're not given. So what we're doing is given only features, right? We're not given any labels, and the goal is so we are not told what to do with the data. All right, we're not told what to do with the data at all. So it's our job to figure out what to do with it. Okay, so can you see structure in this data? And of course you can. So the question is, can you find structure in this data? So that's the ultimate goal. Okay, so this is what's known as a clustering problem. There's more than one unsupervised learning algorithm, but clustering is the one that people relate to the best. Okay, so this is known as a clustering problem because you want to cluster points, or you want to group points into groups where each group has some sort of commonality between all the points. So this is what's known as a clustering problem. And this is actually being used quite often. You probably don't actually know what clustering is being used, but there's a lot of use cases where it's actually being used. So a good example would be, I don't know if you guys visit Google News a lot, but whenever you go to Google News, you see a bunch of news articles. And then each news article has a bunch of links to other news sources that have related articles about the topic. So for example, if you wanted to, see what the latest news for Apple is. So you have an article with Apple, and then underneath that link, you have links to other news providers that talk about the same topic, whether it's BBC News or CNET or anything related like that. So, and a good example would be Google News. Google News. So what Google News does is that it crawls the web and it collects stories, web articles or stories and whatnot, and the job is to group stories that are similar, that talk about similar topics together into one group. So that way, when you go on Google News and you click on the article, you don't have to crawl through the web and find all the articles that are related to that particular topic. It groups all of them into a single group, and then you can browse through all the articles that are related to that particular article yourself, without you having to browse the internet and find them. Okay? So Google News, what that does is that it crawls the web. They are, in nature, this is what they do. So they crawl the web and find similar stories. Well, actually, it finds the most current stories. Okay, and what it does is that it clusters or groups similar stories together. Similar stories together so that you don't have to go and search for them yourself, which is nice. Because if you want to see a different perspective of the story by different news providers, you don't have to remember what all the news sources are. You can just go to Google News and click on each of the links that are related to that particular article you want to look at. All right, so that you don't have to search the web yourself. Okay? So here's a good example. I just took this a couple of days ago. So let's see here. Where's it? Figure 3. So this is what my Google News page looked like a few days ago. All right? And there was this little article from CNET where, you know, this thing here, where they're creating what are known as smart ovens, where there is a Wi-Fi module or which you can actually connect to your oven via the internet, and you can start the oven remotely. So there's an app where you can start your oven, start the timer, or set a particular temperature, and you can start the oven. It's a smart oven, and you can actually control the app via your phone. So it's I think it's a gimmick, honestly, but you know what? If there's a market, if people want to buy it, if there's an interest, then people are going to buy it. All right. So, and then what happens here is that if you take a look, there are links at the bottom of the story where they pretty much all talk about the same thing. So there's Washington Post, CNET, PC Magazine, and so on. So when you click on any of these links, they will give you a page that talk about the same story in a different perspective. So for example, when I took a look at PC Magazine, right, when I clicked on this link, this is the link that I got, or the post that I got, which is here, right? So here's one article, and it talks about Whirlpool machines that integrate Amazon Dash Tech, which is the cloud service that is used to be able to control your oven via the internet. That's PC Magazine, and there's also stuff from IBM Live. There's an article from there as well. So let me take a look. I think it's here. Right. So there's another article too that talks about pretty much the same thing. So. Right, so there's different news articles that talk about the same story. So what the job of clustering is to find similar news stories or similar things that you can group together, and they all share some sort of commonality between them. Okay, so let me just finish off, and then we'll take a break. Okay, so clustering is just one unsupervised learning algorithm. So there's going to be a lot of other unsupervised learning algorithms we're going to talk about, specifically self-organizing maps or genetic algorithms or things that are modeled based on how humans perceive the world. Okay, so clustering is just one problem. Okay, so we will cover some more topics in this area. Later in the course. But clustering is a very good example of an unsupervised learning algorithm. Okay, so anyway, so last but not least, let's end this by saying that unsupervised learning is concerned with finding relationships and grouping things together in a natural way. So you're finding structure you're finding some sort of hidden structure in unlabeled data. So in a natural way. So you are finding structure in unlabeled data. Oopsie. Sorry, data. Okay, and that's the ultimate goal. So another example would be social network analysis. Let's say you're on Facebook or Twitter or whatever social media website you have, and you have a bunch of friends or people you're following, and then what clustering could do would be to figure out if you have similar interests with any of your other friends, and to suggest groups or to suggest ads that might appeal to anyone that belongs to that particular group. Okay? And I think I'll end now, and we'll take a little bit of a break, and then when we come back, we'll actually get into some more theoretical stuff. But I just wanted to give you a brief overview of what machine learning is about, so hopefully that is enough. Okay, so I'll see you in about 10 minutes, come back, and then we're gonna do some more math. Oh, if you haven't picked up a course outline, by all means, please come and pick one up before you go and get a coffee or whatever, and I'll see you after.